Hey guys, wanted to talk about cliff problems. This is kind of a special case of kinematics, and there's really nothing too new here except just trying to learn how to do this. Here are two sets of the formulas that we've seen. We had the big three formulas, and so I've got them here, and those should look very familiar. V equals V naught plus AT, X equals this, V squared equals that. Those are the three formulas. The only thing different about them is that all of a sudden there's little subscripts all over everywhere. So let me just kind of talk you through that. We're separating this into the X direction and the Y direction. When things happen in 2 dimensions or 3 dimensions at the same time, we need to separate that out and say what's happening left to right, what's happening up to down, what's happening forward and back. So that separation there is pretty important. And to help us do that, we put some little subscripts in right there. That X says that that's solely in the X direction, and that this would be the X component of the initial velocity, the X component of the acceleration. Meanwhile, over here, this is Y direction stuff. So the Y component of the final velocity, the Y component of the initial velocity, the Y component of the acceleration. All right. And in practice, we draw a nice, hard, sharp line between these two and separate them off. They have nothing to do with each other. If I stand and I take a rock and I just throw it in my hand, my car keys or something, and I'm just kind of throwing the thing up and down, that's in the Y direction. That my car keys go up and they come straight back down, land in my hand. Now, if I'm also walking in the X direction, that would be separate motion, and I would use these three formulas to tell me where I am on the street and how long it takes to get to the next block and all of that. But I would use these formulas to tell me what's happening with the car keys going up and down. And those two things are happening at the same time, but they have nothing to do with each other than the fact that the time is the same. So if I walk for 20 seconds down the street and throw my car keys, then that time is shared, right? And that's going to be the same amount of time. But other than that, that line down the middle is pretty important. We say that these are independent, which means they have nothing to do with each other. Here's a nice little picture to kind of think about that. What they've done with this is they've taken a stop-action photo of two balls that are released at exactly the same time. The red ball is just dropped, so it's falling straight down, and you can see that the balls are getting farther apart, or the spots where the balls were whenever the strobe camera flashed. That thing is falling faster and faster, covering more and more distance in the same amount of time. So the red balls are getting farther and farther apart. It's really just one ball, but at different times. When the light goes off, that's where it was. And it goes flash, 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 and you get that series of red dots going straight down, moving farther apart as they get as it speeds up due to gravity. Meanwhile, the yellow ball is starting at the same height. It's starting at the same initial velocity. It wasn't moving up or down at the beginning either. It's got to fall the same distance, and you can see that the yellow balls, even though it's getting kicked to the right, even though that it has an X velocity, is falling side by side. That when I look at this picture of the red dot and this picture of the yellow dot, those are side by side, and all the way down, these are just perfectly matched up as that thing falls. The yellow dot has an X component and a Y component. The red ball only has a Y component right there. And that independence is important, because every time something happens in 2 dimensions or 3 dimensions in physics, we separate it out and we say, well, what's happening in X? What's happening in Y? What's happening in Z if you had 3 dimensions? Okay? So that's kind of a typical thing. And we're going to do that here. It's not that hard to do. You're doing the same thing. You're just doing it twice. Do it once in the X direction, once in the Y direction. Here's a good example of that. We're taking a cannon and we're firing this thing horizontally from a 10-meter wall, at 450 meters per second. Okay, so I'm going to draw a little picture over here on the side. I've got this 10-meter wall. Maybe it's a fort wall. Maybe, I don't know why else there's a cannon on a wall. But up here's the cannon. And there's a little cannonball in there. And when we shoot this thing, it pops out right there, and it's moving horizontally. Now, this is an important word. We like this word right here because it makes the math a little bit easier. I'll show you what I mean in a minute. But that ball is going to move horizontally. The initial velocity in the x direction is this 450 meters per second. But I've also got to consider the initial velocity in the y direction. How fast is it moving up or down at the beginning of the problem? And of course it's not, because it's moving horizontally. Now, we've got most of these numbers done. This 10 meters is important here. We drew the wall. So I need to come in here. That would be my displacement. That ball is going to fall straight down 10 meters. So I'm going to write y, the displacement in the y direction, is equal to 10 meters. And just to kind of help me keep this straight, I'm going to put down right there like that. So I know that one. The other thing that I need to remember is that those dots should be getting farther and farther apart because gravity is pulling straight down. That causes an acceleration. So I need to come in here and think about the acceleration in both the x direction and the y direction. Since gravity pulls down, since we know that gravity is 9.8 meters per second squared, at least on here on Earth, and I'm going to put down again just to kind of jog my memory here when it comes time to do the right thing with this. But that's the acceleration due to gravity. That is g. All right, we've seen that before, so no big surprise. But it would look like that. We could call that g if we wanted to. The acceleration in the x direction is 0. And students very often have a hard time remembering that. But let me just tell you for the first time here, maybe not even the first time, that gravity does not pull sideways, okay? Don't put the 9.8 in the x direction. It doesn't pull sideways. Gravity pulls down. It pulls in the y direction. So you got to separate that thing out and get it where you need that to go. All right. I've already put these variables over here. Everything that we know. We just made that list, so you've got it in 2 places here. But I guess the time, I didn't tell you anything about that. But 8 seconds is clearly going to measure the time. In that 0.8 seconds, the ball is going to do 2 things. It is going to fall from this position straight down and hit the ground, and it is also going to move straight to the right pretty fast here. So same old deal. I'm going to have to go a little bit high here just to get out of the range of this thing. Okay, but the ball is here and it's moving 450 meters per second, and it goes across like that at a regular interval. It's not speeding up, it's not slowing down. Those dots should be the same distance apart until it hits the ground. All right? And you say, well, it doesn't hit the ground if it's going straight across. Well, yes, it does, because these dots are getting farther and farther apart. We had that first one right here where you see it. Oh, man. And the next one's going to be a little bit farther down. Guess I should have done this right the first time, huh? Let me delete that. Just do it again. The first one's going to fall a little bit. The second one's going to fall a little bit more. And the next one's a little more. Okay, and I'm kind of doing this by hand, just trying to guess. But if you match these things up, a neat thing happens. If I come over here and like that, well, here's the first red dot and the first blue dot. So they're kind of happening at that same point right there. So let me just kind of put a green dot if it'll let me draw one there. No, it won't. I'll move that over just a little bit maybe. See if I can squeeze this in. No, not you. There we go. All right, this may not work. All right, but let's just give it a try. If I come down where this dot is, and I go over where this dot is, see how those would go right there? It's moved to the right, and it's fallen down. Here comes this one, and that matches up with the third one right here. I get a dot. And I'm going to come down and over and get a dot. Down and over, and I get a dot. And here's that last one, over and down, and I get a dot. That is that curved path right there that we call a trajectory. All right, I didn't do a very good job of that, but I hope you get the idea. That curved path, it's half of a parabola is what it is. And you can see that on that last slide there, right there, where the red line is straight down and the yellow line is making that half parabola, upside down inverted half parabola on the right, speeding up as it goes down in the y direction, but not in the x direction, moving the same distance apart. So that's the trajectory that we're interested in, and I'm going to call all of these problems cliff problems. This one had a wall, so if you want to call it a wall problem, that's fine. But generally, a rock is thrown off of a cliff, a car drives off a cliff, a cannon is shot off of a cliff, a wall, off of a hotel balcony, off of a hot air balloon, a wheel falls off an airplane. All of those collectively can be called cliff problems. And we want to do some kinematics with them. It's the same old kinematics that we've always done. The only trick is that we need to do it twice. Once in the x direction, and say, well, what happened in the x direction? And then we're going to come back and do it again in the y direction and figure out what happened that way. The two are independent, have nothing to do with each other. So, here's my list of variables. I broke them out. All of the x variables are together. The cannon ball is in the air for 0.8 seconds. It was initially moving 450 meters per second. Its acceleration is 0 meters per second because gravity does not pull sideways. We want to know how far it travels in that 0.8 of a second. This is so easy it's not even worth writing down, is it? Here's my formula that has those 4 variables in it. Okay? It's even easier because a sub x is 0. And when I take half times 0 times t squared, that just goes up in smoke. And right here, if I take the 450 meters per second and multiply by the 0.8 of a second, you can see that the seconds are going to cancel out. I have no units left except for meters. And we'll get a number for that real quick here. 450 times 0.8 is 360. Okay? That cannonball is going to go 360 meters to the right. That's its x displacement. Its range is sometimes the thing that we call it. If it hits and makes a big explosion, a big crater right there or something, it traveled 360 meters horizontally from where it left the cannon over to the impact site. Okay? Now we want to do the same thing in the y direction. Well, it's the same formula. Y equals v naught yt plus 1/2 a sub y t squared. I've got different numbers. I'm looking at these numbers because this is the y direction, so I need the y components. How far did it go in the y direction? How far down the cliff is it? This may or may not work. I might have made up bogus numbers here. That 0.8 of a second. Well, I'll tell you what. What we're going to do is find out where it is after 0.8 of a second. And I probably should not have said that it hits the ground because I may not be down at the ground yet. All right? I know I've traveled 360 meters to the right, but I might not be down at the ground. We might be up about here somewhere. All right? So I might have steered you wrong. All right? The initial velocity in the y direction is 0, so I put that right here. I'll put the 0.8 seconds, but you can see that that's going to be a bust right there. 1/2 times 9.8. I'm going to leave the units out just because I'm out of room. 0.8, that's got to be squared. All right, but how far down did it go? I need to say 0.5 times 9.8 times 8 or times 0.8 squared, and we've dropped 3.136 meters. We are not down at the ground. All right, and sorry about that. Let me hit the right button there. 3.136 meters. Let's just call it 3.1 meters, shall we? 3.1 meters is my y displacement, like that. So we're actually somewhere, I would guess about here. Okay? We've dropped about 1/3 of the way down, and we've traveled over this way 360 meters. That seems like a lot, but remember, we were going pretty fast. That's a pretty big speed. This is a cannonball coming out of there that we're talking about. So we could use the x direction equation, the y direction equation. We could find out exactly where that cannonball is, and we could do that all the way down. We could track its position at 2.4 seconds. It's, however long it takes to hit the ground there. I don't think it's in the air 2.4 seconds when I think about it. But that would be one of the questions. How long does that thing spin in the air? And the longer it spins in the air, well, that's due to the height here. That's a y direction question. It's going to fall from here to there. The height of that cliff determines how long it's in the cliff. So if I wanted to know the time that it takes to hit, I'd have to think about the y direction. And if I wanted to know how far it goes to the right, that's x direction. So I'd use those same two formulas, and I would do that. Let's do one. Here's one right here. A rock is thrown horizontally from a 20-meter cliff, this time at 8 meters per second. They have two questions. How long does it take to hit the ground? And how far does it go to the right? So I'm going to answer both of those right now, and you can already see where this is going, I think. We need to separate out the y variables and the x variables like we did. I need to say, here's all my y direction stuff, and here's all my x direction variables, and kind of keep those separate because they have nothing to do with each other. So let's see what we know here. When I throw this thing horizontally, the rock goes this way. 8 meters per second is the initial velocity. I recognize the units, 8 meters per second. And so I'm going to put down here that V0 equals 8 meters per second. But because it's horizontally, it's all in the x direction and none in the y direction. All right? So I need to separate that out like that. I need to know that in the y direction, the initial velocity is 0, and in the x direction, the initial velocity is 8. Okay. I also need to break out the acceleration in the y direction and in the x direction. That's going to be exactly the same as it was before. Gravity pulls down with an acceleration of 9.8 meters per second squared. And there's that little down again. A sub x, gravity does not pull sideways. We're not doing air resistance. We're not doing wind. We're not doing a flying cow that came along and kicked the rock or anything like that. Once it leaves my hand, it's going to keep moving 8 meters per second until it hits the ground to the right, but it's going to speed up as it falls. So we've got both of those in there. All right. Looks like there's one more number here to mine out. That 20-meter cliff, that is going to be the height of the cliff. I don't know what's going on right there, but let me try to circle that number again. There we go. The cliff's height, the y direction, is 20 meters, and that's down right there. And they had two questions. How long does it take to hit the ground? That's the time. So time is a question. I don't know it here, and I don't know it here. they also want to know how far it goes to the right. And that has nothing to do with the y direction. That's down here. So I'm going to put x equals question mark. There's two unknowns in this equation. I can't solve an equation that has two unknowns. This one only has one. I could do this one first. Let's come along in the y direction. Let's write the displacement formula. You can see that's the one I want to use because those are the variables. This formula ties those four variables together, and I've got a formula that works there with my model. I look over there and it says that v naught y is 0. 0 times t is going to be 0, so I get to cross that term out, and that's nice. Anytime we can cross stuff out, it makes our life a whole lot easier. So just throw that one away. It's equal to 0. Like that. All I have to do is to deal with this. Now remember, we're looking for the time. So when I do this, I can solve that directly. What I'm going to do here is multiply both sides by 2. If I come in here and say, here's a 2, that 2 is going to cancel this one on the bottom. Here's an a sub y that's multiplied. I'd like to get rid of that. So if I divide by a sub y, then the a sub y on the top cancels the a sub y on the bottom. But whatever I do to one side, I got to do to the other side. So let's do that same thing over here. And let's see where that got us. At this point, I have 2y divided by a sub y. You could replace that with a g if you wanted to, is equal to t squared. I don't want t squared. I need t, so I'd have to take the square root here. If I do that, I'd have to take the square root over here. The square root of t squared is t. There's the formula that I need to plug my numbers into. And I've got all my numbers right over here, nicely cataloged up, all my y direction variables to put into my y direction formula. So I've got 2 times 20 meters divided by 9.8 meters per second squared, and that's going to be the time that this rock spins in the air. I'd say square root 2 times 20 divided by 9.8, and that's 2.02 seconds. Okay. So we just answered this first question. How long is it in the air? We know the answer to that. Even if they hadn't explicitly asked for that, we usually have to get it anyway. So we kind of have to take that step whether or not they say go get it. Usually we're going to have to do it. Now the nice thing about knowing that number is that we can come over here to our table and fill it in. I know this is 2.02 seconds, but also the time down here is 2.02 seconds, like that, leaving me only one number, and I can solve for that pretty easily. So let's do that one now. The way we're going to do that is to think about the x direction. I'm only going to use these x direction variables, and we've got them nicely separated out. I'm using the displacement formula again because that's the formula that involves those four variables in my list. And it looks like that. I see that a sub x is equal to 0. Anytime you can get rid of some stuff, 1/2 times 0 times t squared is a 0. Add 0, that's nothing, right? That doesn't do anything. The part I'm interested in is this v naught x times the time that I just found. So x is going to be my v naught. That was 8 meters per second, the x component of the initial velocity. The time was 2.02 seconds. And when I multiply, I get something real close to 16. On the calculator, you can just come in here and say times 8, and it'll pick up the last number, 1616. Okay? I don't know how much of that you want to keep, but where's my, here it is, 16.16. I'll put it all down. Second cancels the second. We're left with meters. We're looking for a distance. That's the number that we want. Okay? Now, sometimes people say, shouldn't gravity, since it's down, shouldn't that be negative? Shouldn't we have come in over here and it's going to give me fits, not let me draw this where I want to, probably. Shouldn't we have called that a negative 9.8? And the answer is, yeah, we could do that. But if I do that one, if down is now negative, see how this one also has to be negative? So it's kind of your choice. You can call down negative, but if you do, you have to get all of the downs and call all of them negative. Effectively, what we're doing is creating a little vertical coordinate system here. And it doesn't matter which way you pick. One direction is positive, and anything that points up would be that sign. Let's say up is positive. If I say up is positive, then anything over here in this list needs a plus sign. And the opposite direction would be negative. So anything over here in this list that points down gets a negative sign. And if that were the case, then I would have come in here and said, well, this is a negative 20. And there's no hope of getting that in there now. And this would also be a negative 9.8. And see how the negatives would cancel? So I would still get the same answer. I've done enough of these things to know that I don't really like the negative signs. So if I can pick a coordinate system that will enable me to minimize the number of negative signs, I kind of count that as a good thing. What I did initially, and again, the other way works fine, gives the same answer. But I say, well, I know my initial velocity is down. I know my acceleration is down. I know the distance that this rock falls is down. Everything's pointed down. So I need to either call all of those positive or all of them negative, and it doesn't matter. And I don't like the negative sign, so I just call down positive, and that put me a plus sign right here and a plus sign right there, and I got the answer. If you want to call up positive, knock yourself out, all right? But it does mean that you need a negative here and a negative there, which would put a negative sign right here and a negative sign right there. The negatives would cancel, and you still get the same answer. You need a coordinate system. You need to watch it, especially if you have stuff that's going up and other stuff that's going down. But just draw that coordinate system and then stick to it. Once you've picked either way you want, stick to it. Okay? Here's another problem. It's actually the same problem, but this is the same problem? No. This is that first problem that we were doing with the cannon from the 10-meter wall. So let's do this again. We're going to do the whole process again. The part that you really need to get right is all those variables, and you're going to want to separate them out to y direction and x direction. And there's lots of ways to do this. If you like the picture and you want to draw it in a little picture, that's fine. If you want to make the list, that's fine. But the variables I'm interested in would be v naught y, a sub y, y, t. And then over here, I'm interested in v naught x, a sub x, x, and t. All right? In both cases, I'm trying to use the displacement formula. So in my y direction, the displacement formula looks like this. And in the x direction, the formula looks like this. All right. And you can see that those are the four variables I have up here, so I need to know as many of those as possible. And similarly in the y direction. All right. So we read the problem, we get the numbers, we figure out where to put them all. Here's a 10-meter wall. That is the height of the wall. That's going to be my y right there. And if I put 10 meters, then I need to pick whether that's a positive or negative. Temporarily, let me just put a down right here so that I can see what's going on here. All right. My next number is 450 meters per second. Meters per second is a velocity. So it's either going here or part of it in both. Depends on what's going on. But it says it's horizontal. A horizontal shot means that all the velocity is initially in the x direction and none in the y direction. So I'm looking at that. We've got that one down. That's actually all the numbers that they give me. But I should remember that I'm standing here on Earth. And so I do have acceleration due to gravity, 9.8 meters per second squared. And here again, I'm going to put down to remind myself which way that goes. And the acceleration in the x direction is 0 because gravity does not pull sideways. I'm looking for the time here. One missing variable, we can solve for that. I could bring that time over here, and then I could solve for x. So that's the game plan on this thing. I'm not real sure you can see the green real well, so I'm going to switch to something a little bolder. Should have already done it, I guess. But here we go. I look at these numbers. I'm trying to put them into this formula, solve this thing as easily as possible. The easiest way is to get rid of everything we don't really need. So when that is 0, that term crosses off. Again, multiply both sides by 2. Divide by a sub y. That gives you t squared, but I don't want t squared, so I'm going to take the square root of both sides. If it's a horizontal shot, you always end up right there. If it's not a horizontal shot, you do not end up right there. So be very careful about using that shortcut. This will work for horizontal shots. It will not work for angle shots. We'll see one of those at the end of all of this. Okay? I put in my numbers. I need to think about my coordinate system. Am I okay? Do I want to call it up or down, positive or negative? Here's a little vertical y direction coordinate system. What I did was to call down positive. So anything with a down gets a plus sign. Those two are both down. They both are in the direction marked positive. And so when I come in down here, it's positive and positive, and that'll work. If you don't like that, then call up positive. But these two being down need a negative sign, and you put those negative signs right there, and it'll cancel and give you the same answer. Let's see what that answer is. Come in here. I want to do the square root of 2 times 10 divided by 9.8. That's 1.43 seconds that the thing spins in the air. All right, there's my first question answered. And that's nice because I get to put it here and I get to bring it over here. This is the only thing that's shared between the two numbers. All right, but that means I only have one unknown when I come to this one, so we can solve that just fine. The initial velocity in the x direction was 450 meters per second. I'm looking at these numbers now. The time was just determined to be 1.43 seconds. A sub x is equal to 0. Half times 0 times t squared is 0. That's gone. All I have to do is multiply 450 times 1.43. 1.43 is already there, so I go times 450, and I got my answer, 643 meters. Okay, and we're done. All right, that rock left the cliff moving this way. It kept moving that way, but it also fell, speeding up as it went. It took 1.43 seconds to hit the ground, whether I think about it falling straight down or taking that curved path that we've drawn like that. That's the real path of it right here, but it's made up of this and that. It landed 643 meters horizontally away from where it left the cannon. All right. Now, this is essentially the same problem, so we can steal some of those numbers that we had from the last one, but they ask a little bit different question. So let me get the numbers we just did. We don't need to do it again. Same cliff, same cannon, same cannonball, everything. 1.43 seconds was the time. So we'll put that right here. Like that. X is not what they're looking for here. They want to know the velocity. They want to know how fast is that cannonball moving when it hit the ground. And there's kind of two parts to that. Let's draw the cannonball. It is moving in the x direction, so this will be the final velocity in the x direction, and it's also moving down. Okay, now this isn't to scale. I shouldn't have drawn it that big at all, should I? Might actually be more like this or something. Okay, but we'll find out. The y component of the final velocity. I don't know this number. I don't know this number. And since those are, since there's two dimensions, I have to separate it out and think about each part. I've got my y variables listed right here. Let's put the formula that gives me this. Okay, and there's actually a couple ways we could do it here, but let's forget about this number. Final velocity, initial velocity, acceleration, time. I could come in here with my y direction formula and variables and write v sub y equals v naught y plus a sub y t and solve for that. That'll tell me how fast I'm going in the y direction. This piece right here. We'll come back and get this piece. All right, so this was a 0. My acceleration is 9.8 meters per second squared. Again, decide if you want to call that up or down, but as soon as you pick one, you're stuck with them for forever, or at least for this problem. There's that right there, and I need to multiply 9.8 times 1.43. And let's round that down to about 14 meters per second. That would be my velocity. That's how fast it's moving down. 14.3 meters per second in the vertical direction. But it's also moving to the right. It started out moving 450 meters per second. The acceleration is 0. If you want the gory details, the useless gory details of this, you could come in and do exactly the same formula in the x direction. A sub x is equal to 0. So you can see that the initial velocity is going to be the same as the final velocity. Final velocity in the x direction is 450 meters per second. And now I've got this number right there. And what I really want to know is how fast it's moving with both of those components. So I'm going to draw a little arrow right here. That's its real velocity right there. And you recognize that as a right triangle. I've got two sides of the right triangle. So I could apply the Pythagorean theorem right here. And I would have 450 squared plus 14.3 squared. Yeah, I should have put the units. I'm out of room. And that would be a square root 450 squared plus 14.3 squared. And that's 450.2. That little 14.3 didn't do a whole lot. This number's so big, and next to it, this 14.3 doesn't really do much. I'll put the 0.2 just to kind of show that it's a little bit more. All right. But in that case, I've got to go find the x component, find the y component, and then put those together like that. All right. Now, I think this is our last problem that I wanted to do. Yeah. So the end is in sight, but let me show you what's going to happen right here. This problem is interesting because I have a cliff. It's a cliff problem. And we're going to throw a rock off the cliff. They tell me that the height of the cliff is 20 meters. So I can start making my little list like I always want to do. The y distance is 20 meters. The rock is here. and it's going to fall down. It's going to end up below. So 20 meters down. My acceleration in the y direction, that's gravity, 9.8 meters per second squared, down. When I throw, I need the initial velocity of this thing. Well, the difference here is that now I'm throwing the rock up at a 12-degree angle. So the initial velocity is something like this. I'm sorry, that's an 8. 8 meters per second at a 12-degree angle. All right? So it's not as cut and dried as it was before. I don't have the number. I can't say, well, the y component's 0, because it's not. I have to go in here and say, I want the y component. I need to know this side right there. How fast is it going up? And then eventually we're going to need this side. How fast is it moving to the right? So this would be v naught x, and here's v naught y. If this is my 12 degrees, then you recognize this is the opposite and this is the hypotenuse. And the trig function that uses opposite and hypotenuse is sine. So clearly the initial velocity in the y direction is given by v naught sine theta. And we'd have to go get that number. 8 meters per second times the sine of 12 degrees. We did not have to do this before. This is a new twist on it. If you have an angle shot, there's about 3 extra little steps you got to do here. And this would be the first one. Separate out the x and the y components of the initial velocity. Okay? That's 1.66 meters per second, and it's up. Okay, we haven't seen one of these yet. But you see how when I have up and down, something's got to be positive and something else has got to be negative. So I really have to key in that there's a coordinate system going on here and pick a direction and stick with it. Again, I don't care which way you pick. Most people seem to be more comfortable with positive up, so I'll do that. I like it the other way actually, because again, I don't like negative signs. If I pick it this way, this down gets a negative sign. Down is my negative direction, so the rock falls down in the negative direction. The gravity pulls down in the negative direction, but the velocity, the initial velocity starts out going up. So that's a positive number right there. You got to be very careful with that. I just like to write the down, down, up because it's the easiest way to cue myself, to set myself up to go up. I got to think about the coordinate system. Anyway, we're looking for the time. All right? So let's put that into the y direction, just like we always do, the y displacement formula. Our object here is to get the time in the air. Here is my y displacement formula, just like always. And every time we've done this problem before, v naught y was 0 and we got to cross this term out. It is not 0 here, so we don't get to cross it out. And what that means is I'm going to end up with a term that has t in it, and I'm going to end up with another term that has t squared, and that's what we call a quadratic equation. Okay? Probably the best thing to do at this point is just to go ahead and take these numbers and jam them into your equation here. So I'm going to put negative 20 equals positive 1.66 t plus 1/2. The acceleration was negative 9.8. And you really got to pay attention here and get the signs right, because they do matter. All right? It looks like that. I can't solve that equation with the regular algebra steps that we've been doing. This is a quadratic equation. It's a different game. And maybe you want to go look up quadratic equations in your algebra book, or check a video about it or something. But that's a quadratic equation. There are at least 4 ways to solve quadratic equations. You could try to factor that, but I'm going to tell you right now that those decimals are going to take all the fun out of that. You could try to complete the square. Remember that? completing the square. Most people don't remember how to do that. And again, the decimals kind of make that a little dodgy. So I probably wouldn't go that route. Your two viable options would be the quadratic formula. And the quadratic formula is probably the best bet here. It's what I'm going to do anyway. The quadratic formula looks like this. The variable that you're looking for, t, is equal to negative b plus or minus the square root of b squared minus 4ac. All that's underneath the radical, underneath the square root. And then we divide the whole mess by 2a, like that. So that's worth a little bit of real estate on your index card if you want to have that for the test. Maybe you know this off the top of your head. But that's what I want to use right there. So let's see how to do it. First thing I have to do is to get this in descending order. I need to go find a, b, and c. And a is the number in front of t squared, and b is the number in front of t, and c is the number after I bring this guy over here. I've got to have a 0 on one side, so I'm going to start out by adding 20 to both sides. That would cancel here and give me the 0 that I need on one side or the other. But if I add 20 to the left, I got to add 20 to the right, so that comes over like that. I need the t squared term in first place. Half of negative 9.8 would be negative 4.9 t squared. So he just moved up to first place. This guy is going to fall back into second place. It was positive here. It needs to stay positive. And then I've got that plus 20 hanging on for dear life at the end. Okay? That's the quadratic that I want to solve. I have moved it around until it's in descending order. We're ready to go. I need a, b, and c. A is the coefficient of the t squared term. So I take all this right here, including the sign. And b is the coefficient of the t term. So I take all of this, including the sign. And c is this last number, the constant term, the coefficient of the t to the 0 term, however you want to say that. And I keep the sign with that. All right, the signs are so important. I'm going to check them one more time. This the height of the cliff was down. We elected to call that negative. So I had a negative over here. I had to add 20 to both sides to get the 0 that I've got to have right there. I want to know the time when the height is 0, when it's right there. Okay, so that's why this one's positive. It was positive here, it's positive there, it's still positive right there. All right, right here the initial velocity was up. Up is the positive direction. So I've got a plus 1.66 there. It goes into my equation as a positive number. It's positive, it's still positive. B is positive. All right. And then lastly, this A, now this A is the acceleration and this A is the A from the quadratic formula. So be a little bit careful with that. But my A sub y was down. Down is negative. So when I put that in, I got a negative right there. A positive times a negative is a negative. So half of 9.8 was 4.9, and it's negative right there. It's still negative. I need all those signs to match up right. Okay, we're ready to do this thing, and I don't have a whole lot of room left, and you're tired of hearing me talk, so I'm going to just put the numbers in here. I need to look over here. Negative b. Well, b is positive 1.66, so negative b would be negative 1.66. And then I've got a plus or a minus. We're looking for two answers. There's two possible solutions here. One comes about when we use the positive version, and the other one we use the subtraction sign right there. That is b squared, so don't forget to square it. And then I've got minus 4 times a. A is negative 4.9 times c, right? And that is a positive 20. Close that up and then divide the whole shooting match by 2 times a. Well, 2 times 4.9 gets me back to 9.8. So the easy thing to do is just go negative 9.8. You're always going to have gravity on the bottom. If you want to put 2 times negative 4.9, that's fine. All right, but I'm going to, in the interest of space and time, I'm going to do that. You got to be very careful putting this thing into your calculator. The first suggestion I would make would be to make sure that that whole numerator happens before you divide by g. So to do that, I'm going to put some parentheses right here and right there to make sure that whole numerator happens before I divide by negative 9.8. All right, on my calculator, open up that blue parenthesis, go negative 1.66, watch all your signs. I'm going to do the plus one the first time. I'll come back and do the negative the second time. Here's the plus. I need square root of 1.66. That has to be squared, so hit the squared button. Minus 4 times negative 4.9 times positive 20. Okay? That's my whole numerator except for that closed parenthesis, except when you look up here, see how I've got 1 open parenthesis, 2 open parentheses? I need to close both of those. That one closes the square root, that one closes the numerator, and now I can divide by negative 9.8. All right? You got to learn how to talk to the calculator in its language, and this is going to do it. All right, but there's the time that it says it took that rock to hit the ground. That is one of our possible answers, negative 1.8, or let's just call it negative 1.9 seconds. I think you'll agree that that rock probably did not hit the ground 1.9 seconds before it hit the ground. That's one of the possible answers. That's the wrong one. There will always be a positive number and a negative number. You want the positive one. So that's not the one we want. We want the other one. Let's try it again. I need to put that back in the calculator. Oh, but wait, it's already in the calculator. So I'm going to go second enter. It pulls the whole thing back up, and all I have to do is change that plus sign to a subtraction sign. Use your arrow keys and just stroll right there, change that one sign. It's already in there. And there's the one we want, 2.2 seconds. That makes a little bit more sense. I throw the rock, and 2.2 seconds it hits the ground. That's my time in the air. Okay? That's a whole lot more work than the first one was, right? First of all, we had to break out the x and the y components of the initial velocity using sine. I don't guess I actually got around to doing the x one, but we're going to need it right here real quick. So that would be cosine 8, cosine 12. So that's kind of the first step, is go get those. 7.83. Kind of carrying an extra decimal place around until I get to the end, and then I'll round it once at the end. And okay, but so there's my initial velocity in the x direction. We didn't have to do that on that last problem. We just kind of said, well, it's horizontal, so it's all in the x direction, none in the y. I have to really think about my coordinate system here and make sure that I know what's going up and down, and therefore positive and negative. And when I bring it over and do this, this term does not cancel out, so I can't just solve it directly. I have to do the quadratic mess. You got to be real careful with the signs. You got to be real careful when you put it in the calculator. All right, here on out, we're fine. X equals v naught x t plus 1/2 a sub x t squared. We already know that a sub x is equal to 0, so that throws that out. I need to know the initial velocity in the x direction, which I called up and found to be 7.83 meters per second. I need the time, which I just found to be 2.2 seconds. And I get my calculator back out. I've already got the 7.8 something there, so if I just go times 2.2, then I'll get my 17.2 meters is the distance that goes. Where the seconds here cancel the seconds there, leaving me just meters of distance. So now we know how far out that thing comes and hits the ground, or whatever's there. Maybe this is a ballistics problem and somebody's trying to blow something up, or they throw a rock and it hits whatever. Okay, that's how you do the angle cliff shot, and that problem beat to death, I think. All right, thank you very much. Have a good day, and best of everything.